Hey everyone, what if I told you a few lines of code can detect cancer in your body? Yes, this is not a science fiction. Today you will see how Python code plays a crucial role in detecting disease like cancer. And don't worry, this is beginner friendly. Even if you have never written a single line of code before, no issues. We will use real medical physics concepts, transform data into images, and see how code plays a crucial role in detecting disease like cancer. CT or computed tomography is one of the most powerful tools in modern medicine. So it captures internal images of the body using X-rays from multiple angles. So these machines don't just magically create 3D images. Okay. So behind the scenes, complex calculations and physics simulations are happening. And that exactly what we already replicate with Python in my last video. So please go and check it out. So every day, doctors rely on CT scan to look inside the body to detect broken bones, internal bleeding, and yes, even cancer tumors. Detecting tumor, the scan data needs to be processed, converted, and interpreted. That's where math and code comes in. So we begin with a CT image. However, since we do not have access to a real patient body scan, we use Shepp-Logan Phantom, a standardized test image commonly employed to simulate a cross-sectional view of a human head. So it's like a dummy scan scientists use to test algorithms before using real patient data. Again, we already discussed this in my previous video. Practically, when hundred of X-ray beams entering your body from one side and pass through, so different tissue absorb them differently. For an example, fat, bone, water, they all attenuate X-rays at different rates depending upon their linear attenuation coefficient. Okay, so we simulating this using linear attenuation coefficient of water, bone, fat, and even tumor tissues. Our next step is we convert this data to Hounsfield unit. Okay, so which is like a standardized grayscale used in CT images. For example, water is assigned 0 HU, that means 0 Hounsfield unit. For air, it is minus 1000 HU, and bone can be 800 HU. So this scale helps doctor and physicist interpret the image easily, as each tissue appears with a consistent brightness level depending upon the HU values, no matter which scanner is used. Now comes the exciting part, the segmentation. Okay, segmenting cancer tumor from normal tissue. Once we have the HU values, we write simple logic to separate out tissues based on their HU values. Okay, so for example, if HU greater than 600, it's probability bone. Between 0 to 500, soft tissue. Below minus 500, that's air or lung, you can say. Even in this code, we simulate here a tumor having HU value between 350 to 400, a little denser than soft tissue. So first linear attenuation coefficient of different tissues, then HU values, and then segmenting depending upon the HU values. This is a simplified version of how AI models begin to learn patterns that could indicate abnormalities. So real AI tools are trained on thousands of labeled scans. But the foundation is, the basic principle is what you just saw, math, code, and a little bit of physics magic. If you are interested to know about this AI model, comment your questions. If you want to dive deeper, community on our website, we will make a dedicated video about the how AI model can actually detect cancer in future. So yes, Python isn't just curing cancer alone, but it's absolutely helping medical physicists do it faster, smarter, and earlier. If it fascinates you that something as abstract as mathematics or code can actually help save lives, know that this is only the beginning. So let's do it with Python. Okay, so first thing first, here we used four libraries. One is NumPy. NumPy is used for numerical arrays, linear algebra, interpolation, calculation, integration, differentiation, any kind of mathematical calculation. Then Matplotlib for plotting, mapping, and visualization. And then Scikit-image for our phantom, that is Shepp-Logan phantom, basically a brain image. And also importing the resize for interpolating the various function and changing resolution in some cases. Second is defining the constant. Okay, so here the initial values are height. I have to define, suppose size is 128, then depth suppose 50. Depth means basically the number of city slices. So depth is now linear attenuation coefficient of water. So that is, let's say, 0.19. Then fat equal to 0.16. Then mu bone, that is suppose 0.50. Okay, mu then tumor. So in the case of tumor, spelling mistake. So for the case of tumor, let's say 0.2. Linear attenuation coefficient of tumor, here I am assuming 0.20. Basically, it's a slight higher than water, or slight higher than the soft tissue. Okay. Now I have to create 3D phantom volume. So for this phantom slice equal to resize Shepp-Logan phantom. Spelling mistake. Shepp-Logan phantom. Okay. Then size, size. It should take the same size. Then mode equal to reflect. I hope yes. Size, size, mode, Shepp-Logan phantom. Okay. I have to add another attribute, that is anti aliasing equal to true. Okay. Now it's time to define the volume. So volume equal to stack. NP NumPy. Please call stack. So np dot stack within the bracket phantom slice for in range depth. Spelling mistake again. I hope it will work. Some attribute mistake is there or not, I have to see. Depth I already assigned. I think depth is 50. Okay. So I have to give a comma in that for. Is the attribute. Okay. So we have to map this linear attenuation coefficient to grayscale or the pixel intensities. Okay. So the interpretation is like that. So we will code the same equation here. So for this attenuation coefficient or attenuation map, I guess map would be better name. So AIIN map, okay, equal to np dot interpolate. Please interpolate. First thing is volume. So interpolate the whole volume. Then 0, 1, and then linear attenuation coefficient of fat and linear attenuation coefficient of bone. So why it is like that? Because the fat has lowest linear attenuation coefficient and the bone has the highest linear attenuation coefficient. So that's why I'm giving here the limit. Okay. So fat to bone. So please interpolate this linear attenuation coefficient range to pixel intensities. Okay. So now it's time to convert this linear attenuation coefficient or the pixel intensities into the HU values or the Hounsfield unit. So here HU equal to mu minus water by water into 1000. Okay, so we will use the same equation in this code. Okay, so HU volume equal to attenuation map minus attenuation of water, okay, divided by mu linear attenuation of water, and last into 1000. Okay, so that's it. Okay, let's run it. We will check whether it is working or not. I hope it will work. Okay, it already worked. So let's run it. Here is the problem. Okay, so where is the problem? Resize got an unexpected keyword argument anti. Oh. I think silly mistake. Now it's worked. Okay, this spelling mistake, I guess. Okay, so now we have to extract the middle slice. Okay, so slice index equal to depth by 2 and HU slice equal to HU volume and slice index. Okay, so let's run it again. Okay, then no spelling mistake. Okay. we are going to differentiate here three things. One is bone, one is tissue or fat, and another one is tumor cell, the cancer tumor, depending upon their HU value, so HU range. Okay, so let's start. So first thing is bone mask equal to HU slice, suppose less than greater than 600. So I am giving this command, suppose if the HU value is greater than 600, then segmented it as a bone. So let's say 600 is okay, let's take as a 700. Okay, then tumor mask HU slice greater than 350 and HU slice less than 400. Let's say, just for example. Okay, okay. Now we are going to mask that soft tissue. So soft mask equal to, so I'm going to copy this whole thing, it's much easier. And now we will change the values, the HU slice or HU values greater than 0 and less than, suppose what I can say, 500. Okay, 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 it's done. Let's run it, we'll see any no issues now. Okay, okay, so now fig access equal to plt, plt dot subplots which have a range of 1 to 4, then fig size equal to 16 and 4. Okay, let's say, suppose, then access 0 dot image show bone mask and mapping into the grayscale, so gray. Okay, now x is 0, set title bone greater than 500 HU. Okay, so that's all. Okay, so we have to do this for soft tissue and tumor, so I'm just copying this. So first one is our tumor, so change the values. This one is 1 1, so let's say it is hot, hot. Change this thing tumor 500 to 800 HU. Then again you have to copy it, put it there, change the number for our soft tissue. Okay, and change this hot to pink, let's say. Okay, whatever you can say. So change these values, let's say 0 to 500. This is our soft tissue, soft tissue. Okay, so let's see if anything I missed. Okay, so say bone, problem is so that is tumor mask, tumor mask. This one is soft tissue masking. Okay, so let's run it. Okay, so some problem is there. Okay, okay, got it. So I have to give another command here, that is for ax in axis, in for ax in axis, ax dot axis of whichever of, and the last one is the main command. The problem is coming out for that, plt, every time I have to request this Matplotlib. Okay, so plt type layout, and now plt dot show plt show means please matplotlib show us the picture. Okay, I hope now it will work. Let's run it. Yes, yes, it works. So you can see. Okay, so first I will insert the main bone image or the Shepp-Logan phantom, as you can understand it better. For visualizing this brain image, that is, or this Shepp-Logan phantom, this is plt dot im show Shepp-Logan phantom, okay, which have cmap into grayscale, okay, okay, grayscale. Then plt dot title equal to, let's say, Shepp-Logan phantom. Okay, then plt dot axis of, then plt dot show. Okay, so now if we are going to run it, then it will show the main brain set or that ct image of this brain phantom right here and in the right hand side, and then we will discuss this segmentation. So first run it. Okay, so see, this one is our the Shepp-Logan phantom. So just by taking a look, you can see this surface area is our bone. Okay, this is the skull, and this skull area is our bone. So that in that first image you can see, so it nicely segmented the bone part. Okay, so here is the bone part which have the HU values greater than 500, and in our right corner there is soft tissue which have 0 to 500. So basically this area, and in between this the black one is air. Okay, so now for the cancer cell, in that case, so tumor I already assigned 500 to 800 HU. Okay, so this part is, so now you can understand, or you can see, or you can predict the tumor position in that patient body. So now you know the tumor position is in between this area or this area. Okay, because here the HU value is larger than the soft tissue and the less than the bone, which I already assigned for this cancer tumor. Okay, so this is the basic model. So like this, what you can do, you can assign different HU values for different body parts. Okay, and then you can see all that body parts differently, and also the cancer tumor. So then you can predict the cancer tumor cell position very nicely. Okay, so this is our basic concept for segmentation. If you want to know more about this algorithm, more about this segmentation, and how that AI algorithm works here more deeply, then let me know in the comments. I will make a different video for that. Okay, so take care and bye bye. I hope you understand it.